In this video, I want to think carefully about one idea, the dot product. By the end, I hope this idea feels simpler and more connected. So, what is the dot product? By the definition, we can define the dot product like this. So, there's a vector v equals v1, v2, until vn. And there's another vector u is u1, u2, un. So there are in n dimension are n. The dot product of v and u is just equal to v1 times u1 plus v2 times u2 plus and so on and until vn times un. That's it. This is the dot product. We just multiply each corresponding component of two vectors v and u. So in two dimension, for example, in R2, for example, let's say there's a vector v equals v1 and v2. And another vector u in this case, is, as you can expect, just u1 and u2. And the dot product between two vectors v and u is just equal to v1 u1 plus v2 u2. That is it. Very simple. Now I want to talk about the angle between those two vectors u and v. So basically the dot product and the angles. Let's say there's a vector u and v in n dimension. Let's say vector v is like this direction and this magnitude. This is vector v. And there's a vector u in a different direction, like this. Let's say this is vector u. And there's an angle between them. We can denote it as theta. And the remaining angle, except the theta, is just 2 pi minus theta. So what does dot product tell us? The dot product, it tells us how much those two vectors point in the same direction. So we are focusing on how much the same those two vectors are pointing. As you may already know, there's a really famous formula when it comes to the dot product, which is u times u dot v is equal to the magnitude of u times the magnitude of v times cosine of theta, which the cosine is the angle between them. Let me write it as uv is equal to the magnitude of u times the magnitude of v times cosine of theta. I kind of want to derive this formula. Let me show you. But before we derive it, we kind of need to know the law of cosines and law of sines. Let's talk about law of sines and law of cosines. We don't have to talk about them that deeply, so I already wrote them down here. So law of sines is just basically tells us the ratio between the angles of the triangle and the lines, the corresponding lines. So by the definition, law of sines is sine of A, the angle here, over the line A, which is facing the angle A, is equal to, the ratio is equal to sine B over B equals sine C over C. That's it. And law of cosines, which is more important to derive the dot product formula, it kind of seems like the Pythagorean theorem, it is c squared equals a squared plus b squared minus 2 times a times b times cosine of c. B squared is equal to a squared plus c squared minus c times a times c times cosine of b. Lastly, a squared is equal to b squared plus c squared minus 2 times b times c times cosine of a. That's it. So we just learned about the law of sines and law of cosines. Now we can derive the formula of the dot product. Alright, so let's get back to the dot product problem. I want to derive the formula now using the law of cosines. So let's say there's a vector v and u, vector v and vector u, theta, and we can draw another line here, this direction, that is u minus v. Using this, we're going to derive the formula. So u times v, the dot product, is equal to the magnitude of u times the magnitude of v times cosine of the angle between them. Using this formula, we can say this u minus v, the magnitude of u minus v squared is equal to the magnitude of u squared plus v squared minus 2u v cosine of theta, right? Now we can rewrite it as u minus v equals u times u plus v times v. It is just a rewritten form, minus 2 times u v, the same cosine. Now, using the kind of algebra skill we may have already learned during middle school or elementary school, I don't know, this is equal to u squared minus vu minus uv plus v squared. This is equal to, the right hand side is the same. And this is equal to, v times u is just the same as u times v because multiplication is commutative, and the vector multiplication is also commutative. So this is the same, so we can subtract them. So we can rewrite it as u squared minus 2, let's say uv, plus v squared. And this is equal to the right term, equals u times u plus v times v minus 2 times u times v times cosine of theta. As you may be able to see, u squared and v squared is just equal to u times u and v times v, so we can cancel them out. Cancel them out. And let's see. So now we're almost done. We can also multiply the both sides by negative 1 over 2, 1/2. Then we can cancel these minus 2. Then we get uv is equal to the magnitude of u times the magnitude of v times cosine of theta. All right. Oops. We just derived the formula of the dot product. Now let's talk deeply about how they represent, and let's talk about the angles. We just derived the dot product formula, so we can say the dot product uv uv is equal to u1 times v1 plus u2 times v2 plus and so on until un times vn. And this is equal to the formula, the magnitude of u times the magnitude of v times the cosine, which we just derived. And using this formula, we can also find the angle between two vectors u and v. So the angle theta is equal to the arc cosine of the dot product uv over the magnitude of u and v. I just multiplied both sides by 1 over the magnitude of uv to get rid of that. So using this, we can also find the angles. Now I want to talk about the dot product and orthogonality. In this course, I want to use the term orthogonality rather instead of perpendicularity, because when we use perpendicular, something is perpendicular in 2 dimensions, not 3 dimensions or more. Because we are talking about multivariable calculus, which means may be multiple dimensions, so it is a better way to use the term orthogonality. Anyway, so when the dot product is 0, let's say u times v is 0, that means the formula u v cosine is also 0, right? Remember, cosine is 0 when the angle is 90 degrees. So this theta is 90 degrees in this case. This is very important concept when it comes to the dot product, because we can notice in 3 cases. So when dot product is greater than 0, that means the angle, acute, right? And when the dot product is equal to 0, if the angle is a right angle. And when the dot product is less than 0, if the angle is an obtuse. All right, so using the property of the cosine, we can figure out whether the angle is an acute, right, or obtuse angle. Now, I want to talk about vector projection and component. We are almost done, but yet I really wanted to talk about this topic because this is really important. So, what is vector projection and vector component? Both ideas answer the same question. How much one vector lie in the direction of another vector? So there's a vector u and v. So let's say I want to know about vector projection of vector u onto v. Then how much of vector u lie in the direction of vector v? Very simply, a vector projection only vector projection gives us a vector. The output is a vector which has the magnitude and the direction. But while the vector component only gives us a number, which is a scalar. So that's the key difference. Let me show you visually. So let's say there's a vector v. It's a horizontal vector, like this. And there's a vector u, this direction. And we are only interested in about this part, only this part. This is the vector projection or vector component of, I forgot to denote it here, u, of u onto v. So there's angle theta. So we only want to know the length or also the direction of this, this part. I put it as a pink colored pen. So by the definition, the component of vector u onto v, component of u onto v is equal to vector u times v over the magnitude of v. So basically you can think of it as the vector u times the unit vector of vector v, which only has the magnitude of 1, but the same direction as the vector v. But the projection of vector u onto v is equal to u times v over the magnitude squared times v. So by the definition, this is the component, vector component and vector projection. We can also derive this projection. For a component, you can kind of see how we get this, but only seeing this formula of the projection, it's kind of hard to understand why, like how we get this. So let's say to get the projection, it gives because it gives the direction and the magnitude, we need to multiply the direction, the vector, and the magnitude. So what I'm saying is I want to know this length and also the direction. So we can find the length of this part we're interested in by using Pythagorean theorem. So because this is the vector u, this part is just equal to the magnitude of u times cosine. And also we know the unit vector of v is just v over the magnitude of v. So we can think of it as the projection of u onto v is equal to u times cosine times the unit vector of v. You need to note that the cosine is equal to the dot product of uv over the magnitude of uv by the definition of the dot product that we just learned. So we can, that means we can substitute this cosine by this term. So this is equal to u times uv over uv times v over the magnitude of the v. As you can see, we can cancel them out, some of the component. So u cancel. There's no more terms to cancel. So this is equal to u dot v, this is the dot product, over the magnitude squared times v. That's how we get the projection equation. So we just learned what vector projection and what vector component are. Alright, so today we explored about how dot product let us find the angle between vectors, how projection works, and how we can break down the vectors into components. It's a super useful tool whenever you are working in physics, engineering, or, I don't know, 3D graphics. Next time we'll take a step further and talk about the cross product, which not only gives us a new vector entirely, but also reveals things like area, torque, or rotation in 3D space. So until then, let's keep things simply connected, and I will see you there. Thank you.